So thanks a lot. I'm going to try to not go over my time. 10 minutes is short and very long for a mathematician. So today I wanted to talk about balls that tile a plane. Initially, I announced spheres that tile a plane, but it's just because for me, balls and spheres are more or less the same thing. To me, balls are a measurable version of spheres. Anyway, I will tell you what I mean by balls. So this in my world is a ball, and I will tell you why it's a ball. So this is a square. I drew a square in the plane on your piece of paper, nothing fancy. What I meant is that if you just go, if you measure the length of the red segment and the length of the green segment, well, the red segment should go all the way to 0. They have the same length. But this is the question. What is really a ball? So here I gave you an actual definition, which is the ball is the elements that have distance less than or equal to r from a given point. And the sphere is actually the boundary of the ball. In math, I tend to think about balls more than spheres, but this is just a personal taste. The theory I'm working on as a research, I could do exactly the same with spheres. It would be just more technically difficult than what I usually do, but it's really a matter of taste. So today is going to be balls. So the shape of a ball depends on the underlying metric, because here I said I was measuring things. And so it really depends on the underlying metric. If you take the Euclidean metric on your piece of paper, which is really what you measure on your ruler, then your ball is going to be round like this. And if you take what we call the taxicab metric, then your ball is going to look like a square. So let me just tell you a little bit about the taxicab metric. Here you might recognize New York City, because we all know that New York City is the center of the world. And so if I zoom in, that's the Upper East Side, I see this grid. And if I turn the grid a little bit, I can model this grid by, we approximate the grid with a standard grid from our plane. And why is it the taxicab metric? Because what's going to read on your meter on a taxicab is just depends on the length of this path. So if you go like this, or if you go like this, it's going to be the same. And obviously, depending on which city you are, the taxicab might do this and rip you off, but that's another metric. But theoretically, the metric you get is really the length of the path that the taxi is going through. And of course, this is kind of a bad model if you know New York City, because this assumes that streets are the same length as avenue, which if you've ever walked in New York City, you know it's absolutely not true. It's not square. Right. Okay, so for some metrics, the balls don't tile the plane. And you can see with round balls, if you try to tile the plane, you would end up having those little green pieces that you can't cover. But however, if I look at the taxicab metric, since I had a square, it will tile the plane. And for some other metric, they do. This is what I call the SL3 balls. I'm not going to talk about it. If you want to discuss the SL3 balls, I'm very happy to discuss it. Those are hexagons, and I call them the SL3 balls because they come from flats in a group that I regularly study, which is SL3R. Okay, so, right, and this is your ball, and you can see that if you move your ball here, you're going to get a perfect tiling. And now if you think about it a little more, and it's like, well, what other regular shape can I use to tile the, what other balls can I use to tile the plane? It's kind of it, because if you have a flat plane, in your tiling, you go around, you need to have 360 degrees, otherwise you're not flat. But if we could go to other type of planes. For instance, the hyperbolic plane, which I don't expect everybody to know, although I know that a lot of people here know the hyperbolic plane pretty well. If you try to glue 4 pentagons at each corner, you very quickly see that you don't have the space to do it flat. You have to wrinkle your pentagon, and if you go around a corner, you get more than 360 degrees. This is what we call negative curvature. And here, you cannot do it flat, but you could do it with a piece of cloth. So this picture maybe doesn't show very well, but I have an actual model where I stitched the pentagons. So you also have a round sphere in the hyperbolic plane, but all n-gons will pave your hyperbolic plane. And here I have an example where I paved the hyperbolic plane with an 8-gon, and you can see you can also express it as a ball, and it will tile your plane, and it becomes smaller and smaller because that's the way we have to show negative curvature. When you want to put it flat, you can't do it by respecting the distances. And what do we do with those tiling of balls? We actually take those shapes and wrap them around. Here you can see how it wraps around to get a genus 2 surface. And this genus 2 surface will have a fundamental group which will tell you how the tiling actually works. Because you see the tiling with squares, there is a way to move the tiles so that you get the whole tiling. And this will explain you how you can move the tiling to get the whole plane. And this geometry is also observed in nature. The hyperbolic geometry is also observed in nature underwater. And the geometry of the lines underwater, because of the increased pressure, the lines did do this half circle. And if we just reverse it, then we have a model of the hyperbolic plane that this is the model I gave you before with the wrapping around, and right, this is how we see it. But you know, if you know it, great. If you don't, it's not the place to learn it. Right. And sending those balls to infinity in dimension greater than 3 are called horoballs. And we have a few specialists here of horoballs. And it uncovers a world of geometrical pattern. And I showed you here one of those geometrical patterns you can get. This is a 3-dimensional hyperbolic space. And we remove here, I show how you can remove a bunch of balls at infinity. And of course, I can only represent finitely many balls, but there are infinitely many. And when you remove them, you can see some kind of geometrical pattern that arise and that we describe as the fundamental group of this 3-dimensional manifold. Right, so this is like an illustrated, this is my illustration of a 3-dimensional hyperbolic space with those balls at infinity, which are balls that have some type of radius, but the center goes to infinity. And I guess that's all I had to say.